It would be f of x times, now you can't say x because x is a single point, isn't it? So x by itself has no width. So how about just calling this little thing delta x? So like if I had my interval, here was 1 and here was 2, if I had cut it into two rectangles, each one would be 1 unit wide. If I cut it into 3 rectangles, each one would be 1/3. If I cut it into 4 rectangles, do you understand? So I'm going to call this the change in x. That's basically my width. So the area of this is equal to that. And how do I find the area of the whole damn thing? I add all those rectangles up forever, right? I draw an infinite number of rectangles and I add them up forever. And that process of taking the sum as k equals 1 to infinity of each rectangle times its width and letting the number of rectangles go to infinity. So you're not going to be tested on this formula or anything like that. I just want you to understand this. What this is, right here, that's the area of one rectangle, isn't it? I'm going to add them all up. How many of them am I going to have? How many rectangles am I going to have? N of them. But then what am I going to let happen to n? I'm going to let the number of rectangles go to infinity. If you do this, this gives you the true area. Okay? Now, here's the big eureka thing, kind of. This right here, we don't like to write that over and over and over, so we have a shorthand notation for it. It is this. Now, this right here is called the integral sign. This function right here is called your integrand. And this right here is called your differential. And the differential becomes very important later on. Right now, it's really just the width of the rectangle. Okay? That's where it comes from. That delta x, that dx comes from the delta x. This f of x comes from that. And this integral sign is basically all that crap right there. Now, the integral sign, you could almost look at it as an s that's been stretched, right? Like an s that's stretched out. That s is kind of like the sum, the sigma. Okay? It's an s that's stretched. So the integral sign actually comes from the idea of an infinite sum. The limit of an infinite sum. All right. Y'all okay with this? Now, I think now is where the whole big result of today comes into play. It turns out, by what's called the fundamental theorem of calculus, which I'm not going to prove in this class, okay, that we have some very, very nice relationships between that sum and the antiderivative. Okay? There's some very, very nice relationships. First of all, the first thing I want you to know is that if we're given a function like this, little f, and we're trying to find the area from A to B. Okay, so if we're trying to find that area, we already know it's that limit n goes to infinity, infinite sum of all those rectangles, right? But the fundamental theorem of calculus says this. It says that that integral And now I'm going to add something to this notation. A and B on the top and bottom. Those are called your limits of your integral. That just tells you where you're starting and ending your function. That right there, if you want to know that, figure out and calculate that area exactly. It's equal to capital F of B minus capital F of A. What's capital F? An antiderivative. This is a huge theorem. Like I said, I'm not going to prove it. We're just going to use it. It's saying, it's really remarkable what it's saying. It's saying if you want to find the area under a curve between 2 points, all you have to do is what? Find the antiderivative and then plug in B into it. Subtract from that what you get when you plug in A. And you have the answer. It's pretty amazing. And then from that, we have this other thing that I want to write down. Because of the relationship between the derivative and antiderivative, do you remember how I kept on asking you before in those examples? I kept on saying, find the antiderivative of this function. Find the antiderivative of this function. Find the antiderivative of this function. Instead of writing that over and over, if you just write this right here, really, if you write the left side, then that's just asking you to find the antiderivative of a function. That's all that means. So we have two things here. An area, number one, has to do with areas, and number two is just like how to ask someone to find an antiderivative. So I think it's time to do some examples. All right? We're almost done. I know it's sad. Example. Find so what am I asking you for? Just find the antiderivative of that, right? That's all that means. This dx right here, don't get all freaked out by that. All that dx really does for you right now is just keeps track of your variable. Okay, your variable in the problem is x. So you're really trying to find the antiderivative of x to what power? -1/2. And using that rule we just used, right, 1 over n plus 1, x to the n plus 1, this should be equal to 1 over, what's n plus 1 here? -1/2 plus 1, which is 1/2, x to the 1/2 again, plus some constant, right? But that's really, 1 over 1/2 is really 2, and what's x to the 1/2? Square root of x, plus a constant. Does everyone see that this is just another way of me asking you this question? Find general antiderivative of f of x equals 1 over square root of x. Does everyone realize that what I highlighted in yellow there is basically me asking you the exact same questions down there, but without having to write all those words out? Yes? Okay. Just remember to add, always put your plus c. I'm not a huge like, oh man, you forget to add plus c and I'm going to count it all wrong, but I know that there are instructors that will count the entire problem wrong if you don't put the plus c. That c is called what's called the constant of integration. All right, so check this out. Next example. Find the area under f of x equals x on the interval 0, 2. So in terms of calculus, here's what I'm asking for. The integral, the way we say it's the integral from 0 to 2, what's the function I'm trying to find the antiderivative of? X dx. Now, according to the fundamental theorem of calculus, what I need is the antiderivative at b minus the antiderivative at a, right? That's what I need. I put it in red just to remind you of what you actually need to find now. What is the antiderivative of x? Antiderivative. It's 1 over 2 x squared. So I'm going to put a little side note over here. I'll do it in green. Capital F of x is 1 over 2x squared, right? That's the antiderivative. Any questions on where I got that? But don't I now have to plug 2 into it and then subtract from that what I get when I plug in 0? Yay or nay? Yes? Okay, now, because we do this a lot in calculus too, let me show you the way that we normally do it. What we do at this point, instead of writing down f of b minus f of a, capital F of b minus capital F of a, what we do is we write down the general antiderivative. Okay? Just like that. And then what we do is we put a line behind it, and we put 0 and 2. And what that allows me to do is not have to write it on the side like I did in green. I'm moving through this problem. I say, okay, what is this? Okay, well, I need the antiderivative. Here it is. And then I've got to plug 0 and 2 into it. But I actually plug in 2 first and subtract from it what I get when I plug in 0. So I'm going to write down here now 2 sets of parentheses. This first one will be capital F of B. The next one will be capital F of A. So plug 2 into that, and what do you get? You get 2, right? And plug in 0, and you get 0. Agreed? So the answer is 2. On top, yes. Yeah, I should probably label this over here. This is your B, this is your A. Or if you want, A and B are the endpoints of the interval, 0 and 2 up there. Now, I made this problem extremely easy because I wanted to be able to verify it with the picture. The function we had was the identity function, wasn't it? F of x equals x. And we were looking between where and where? 0 and 2. What's the value of the function at 2? You plug in 2, you get out 2, don't you? And I wanted the area in here. But that's a rectangle. I mean, that's half a rectangle, isn't it? Or half a square. What's the area of the entire square here? 4, right? 2 by 2 square. But since it's the identity, it's diagonal, so it's half of that, so the answer is 2. I just wanted to show you that it works, right? And it's not a coincidence. It works all the time. Let's do another one. Do you want to break? You want to break before we do another one? Yeah? Let's take a break. 10 minutes. We'll come back. It's just starting to get fun. All right, so look. What we have here is a wire. It's 10 meters long. You're going to cut it somewhere, right? So I'm going to cut it, let's say right here. And therefore the distance from here to here, we'll call it x. And therefore, the distance the rest of the way is 10 minus x. Does everyone see why that's true?